The second approach to testing Plutus contracts I want to present today uses a concept called property-based testing. And that is quite a revolutionary approach to testing that is much more powerful than simple unit testing. And it originated from Haskell, and Haskell, due to its pureness and its immutable data structures, is particularly suited to this approach. But it has been copied by almost all other programming languages by now. So you get property-based testing libraries for Java and Python and C# and JavaScript and many more. And one of the inventors of QuickCheck, which is the most prominent and was the first library using this approach, is John Yu, who is also one of the original inventors of Haskell. And he and his company actually worked with IOHK to provide special support of this approach to testing Plutus contracts. But before we go to that, let's first look at vanilla QuickCheck for pure Haskell programs. In particular, property-based testing subsumes unit tests. So unit tests are just a special case. So we can have a very silly, simple unit test, something like simple prop, just of type Boolean, something like 2 plus 2 equals 4. Let's say ints. And if I import QuickCheck, then I can test this property with the QuickCheck function. And QuickCheck tells me it's okay, so the property is true. If I modify it and make it false, then it fails. Of course, that is not very exciting. Oh, by the way, I see the convention is to call these QuickCheck properties prop underscore, not the way I did it. Let's change that. Let's also make it correct again. Now to see a more interesting example, here's a implementation of a sort function, sorting list of integers, which is using insertion sort, which of course is not very efficient. So the idea of insertion sort is you sort the tail of the list and then insert the head of the list at the right position. And this is a buggy implementation. And in order to test it, for example, a property that we could test would be after applying sort to a list of integers, the resulting list is sorted. So I define a helper function isSorted that checks whether a given list of ints is sorted. So the empty list is sorted, a one element list is sorted, and a list with at least 2 elements is sorted if the first element is less than or equal the second element, if recursively the tail of the list is sorted. And using that, we can now provide a QuickCheck property like this, that is not just simply of type Boolean, but instead is a function from list of ints to bool. So you can read that like a specification or like a mathematical property. Basically, it says for all list of integers, xs, if you apply sort to it, then the result should be sorted. And QuickCheck can deal with such properties. So I can try that in the REPL and apply QuickCheck to this new property, sort sorts, and it fails, and it gives me a counter example. So it says for this list XS, this property doesn't hold. So if I sort it, the result is not sorted. So I can try that out. And indeed, I get 0 minus 1, which is indeed not a sorted list. And in addition to that, it also seems to have lost an element somewhere on the way. So how does QuickCheck do that? So if you provide a function with one or also more arguments to the QuickCheck function, it will generate random arguments for the function. So in our case, because we have one argument of type list of ints, QuickCheck will generate random list of ints and then for each of these random lists, check whether the property holds. And if it does, then the test passes. But if it doesn't, it will report the counterexample. However, we see that here in this error report, it says after 8 tests and 4 shrinks. So this means QuickCheck tried 8 random integer lists and then found a counterexample where this property didn't hold. But then it didn't simply report the list it had at that point, but it tried to simplify it, and this is called shrinking. And that's also a very powerful feature of QuickCheck, because often the counterexamples, the random counterexamples that QuickCheck finds are very complicated, very long lists with very long numbers. But then once a counterexample has been found, QuickCheck tries to simplify these counterexamples. So in the case of list of ints, it might try to drop an element of the list that it found as a counterexample and check whether the property is still violated, or maybe make some of the numbers in the list smaller until it doesn't find a way to get an even simpler example. And this is really very powerful and very useful, because if you want to debug, it's very important to have not only a counterexample, but a simple counterexample, as simple as possible. So it's this combination of random test generation and shrinking that makes QuickCheck so tremendously useful. And actually we can see what types of random lists QuickCheck generates. There's a function called sample, and this looks a bit weird, but bear with me. So the way QuickCheck does this random generation is via a type class, and the type class is called arbitrary with capital A. So we can actually ask for information on the arbitrary class. And we see there are lots of instances already. And we see it has 2 methods. One is called arbitrary, one is shrink. So arbitrary is of type gen A, and gen is yet another monad. And basically what it allows is it allows random number generation for values of type A. So it has various methods provided by the monad that allow you to do random generation. And the second method is shrink. So given an A, provide a list of simpler versions of A, whatever that means. That depends on the type, of course. And as I said, we have lots of predefined instances for this arbitrary class already. So in particular, we have one for int somewhere. And given an arbitrary instance for A, we also have an arbitrary instance for list of A's. And therefore, QuickCheck knows how to generate random ints. And now if we look at the result of the sample function, that just in I/O provides some of the random int lists that QuickCheck would use. And there we see something interesting, that the further we go down in the list, the more complicated the list becomes. So the first random one is just the empty list, and then we get 2 with just one element with quite small numbers, -2 and 0. And then we get longer lists, but the elements here are still only 1 digit, and we get simple ones again, but towards the end we have like long lists with quite large numbers. So in addition to just providing random generation in this gen monad, there's also a concept of basically complexity. So not only if you implement that actually by hand, then you're not only supposed to somehow generate a random A, but also a random A of some sort of complexity. So a simple random A or a more complex random A. And then when QuickCheck actually checks a property, it starts with simple random arguments and then makes them more and more complex over time. And by default, it tries 100 different random arguments to a given property, but that can be configured. So I think 100 is a good default for development, but probably for production, especially for complex properties, something like 1,000 or even 10,000 is maybe more appropriate. So that can be configured. Okay, and so we see that this random generation for int lists work, and in our example we found this counterexample 00 -1. And if we inspect the code, it's quite obvious that there's one bug here, because all we do for a non-empty list is insert the first element into the tail, but we don't recursively sort the tail. So we can try to fix this and test again. And now it doesn't find a counterexample anymore. So this property now seems to be satisfied, at least for the 100 or 200 test cases we tried. However, if I try the original counterexample that we found before fixing this bug, we see that we still, we get a sorted list now, but it's of course still not correct. And this leads to an important point that obviously QuickCheck can't do magic. So the results are only as good as the properties we provide. And what we see here is that this one property we have, prop sort sorts, is not strong enough to detect whether the function is actually correct. So in this case, we do get a sorted list, but it's still the wrong result. So for example, we could add a second property, prop sort preserve length, which states that after sorting, the result should be as long as the original list. So what we could say is, for example, length sort access equals length access. If we try this, then we do find another counterexample, 0, 0. And if we check sort of 0, 0, we see we only get the one element list. And the bug is here, because if x is less than or equal y, we append x to ys, but we forget about the y. So let's insert that there and try QuickCheck again. And it works. But of course, that is still no proof that our function is correct, because these two properties together, that actually the result is sorted and it has the same length as the original list, is still not enough to fully specify a sorting function. For example, the sorting function could simply return a list of the same length where all the elements are 0. So that would be sorted and it would have the same length, but obviously it wouldn't sort the original list. So it's quite an art to find properties that are strong enough to basically guarantee that if they are all satisfied, there is no bug. But nevertheless, this QuickCheck approach is much more powerful than traditional unit testing, because it tests so many hundreds or thousands of random test cases and often finds examples that a human programmer that writes unit tests wouldn't have thought of. And with a few lines of code now, these two properties that I provided, I test hundreds of thousands of scenarios, which is much better than just writing 2 unit tests for specific lists.